Hi everyone. So today we're going to be looking at finding the inverse of a matrix. You can think of this like matrix division. So previously we went over matrix multiplication and we had something like this. So matrix multiplication. It was something like we had A times B. So we had the example of a square matrix A times a square matrix B, and this gave us another matrix C. Okay, but what happens if we want to divide by A? So this is matrix multiplication. What about matrix division? Okay, well, we'll see that we can't do this for all types of matrices, only certain types. Okay, so the idea is to take this matrix A and move it over to the other side. Okay, undoing that multiplication that we've done there. So just a little bit of notation before we carry on. The way we're going to be thinking about this is like the following. If we have 2 times 3 is equal to 6, for example, if we want to take the 2 over to the other side, we want to divide by 2. But the way I want you to think of it is multiplying by the inverse of 2. Okay, so with multiplication, the inverse would be 1/2. Okay, because 2 times 1/2 is equal to 1, and that undoes the multiplication. So the way we're going to think of it is instead of dividing by 2, we're going to multiply by 2 inverse. Something like that. Okay, so 2 to the minus 1, you know that's 1/2, and that undoes the 2 with respect to multiplication, of course. So this just equals 1. Okay, so we undid the multiplication there. We're going to do a very similar thing for matrices here. So we find what's called the matrix inverse. It's like this 2 to the minus 1, and we're going to multiply it on both sides. So we are going to find the inverse, or more technically, multiplicative inverse. Okay, because we're trying to invert the multiplication, so multiplicative inverse. Let's just fix that B. Okay, we're going to find the multiplicative inverse of A. Sorry, capital A. And multiply this on both sides. Okay, and we're going to use a very similar notation. So the multiplicative inverse of 2 is 2 to the minus 1. We're going to use the same notation. Now, it doesn't mean 1 over A. It's just a notation that we use to describe the inverse. So it's just a way of writing it. It doesn't mean 1 over the matrix. Okay, so notation of it. If we have A times B is equal to C, and we want to take the A over, we multiply by A inverse, which we write as A with an exponent of minus 1. Now, again, it's not a real exponent. The whole thing is just a symbol, which means the inverse of A. Okay, so this is not 1 over A. Okay, it's not like working with numbers like that. Okay, and then we can multiply by A. B is equal to A inverse times C. So we have to do the same thing to both sides to maintain the equation. And now we get the very similar thing to before. So 2 inverse times 2 is 1. So A inverse times A is going to be the identity matrix. Okay, so the identity matrix, remember we discussed this last time, it acts as like the 1 with respect to multiplication. So A inverse times A, it's the identity. You can think of it like a 1 times B Sorry. Sorry, my pen's not working. Just give me a second, please. Okay, there we go. So we have the identity times B is equal to A inverse times C. But remember from last time, the identity matrix, when multiplying onto another matrix, it doesn't do anything. So in fact, we could just leave it out and we could write B is equal to A inverse times C. Okay, and now we have an expression for B. We have successfully undone the multiplication by A. Okay, so we have something like that. Now, if we wanted to do the undoing of multiplying by B, we see that B is on the right-hand side. So instead of multiplying on the left-hand side by B inverse, we need to multiply on the right-hand side by B inverse. Because remember, the order of multiplication is very important with matrices. So A times B is different from B times A. So if you do a right multiplication or a left multiplication, those are different things. Okay, so let's just look at this one. So if I have A times B is equal to C, and I want to undo that multiplication by B, I need to do a right multiplication by B inverse. So it's going to be A, B, B inverse is equal to C, B inverse. Again, I have to do it on both sides of the equation. Now, B times B inverse, again, they undo each other. They just give us back the identity. So we have A times the identity is equal to C times B inverse. Again, the identity, it doesn't really do anything with regards to multiplication. So we can just leave it out. And we get A is equal to C times B inverse. Okay, so in the first example, we did left multiplication by A inverse. In the second example, right multiplication with B inverse. Okay, and the thing just to remember, A inverse A, or you can do it the other way around. A times A inverse is equal to the identity. And in the second example, we can have B times B inverse, which is the same as B inverse times B, and that's going to be the identity. Okay. Any questions so far? Okay, so remember what I said at the beginning, you can't find the inverse for all matrices. So only some matrices are invertible or have an inverse. So when do we know if a matrix can or can't be inverted? So a matrix, let's say M, can be inverted if the determinant of M is non-zero. Okay, and then just a little bit of terminology. If the determinant of M is equal to 0, the matrix M is called singular. Okay, you might see that come up. Okay, so non-invertible matrices, those are sometimes called singular matrices. Okay, so we just check the determinant. If the determinant is non-zero, then we can go ahead and find the inverse. Okay, so how do we find the inverse? We're going to start with the 2 by 2 matrix. Okay, it's the simplest square matrix. And then we're going to look at a 3 by 3 matrix. Okay, so finding the inverse of a 2 by 2 matrix. Okay, so if we have a 2 by 2 matrix, A, B, C, D, and we want to find the inverse, we first need to check the determinant. So the determinant of A, B, C, D is given by AD minus BC, and we need to check that this is non-zero. Okay, so that's the first thing we need to do. The second thing, now this is only for a 2 by 2 matrix. What we do is we take 1 over the determinant and we multiply by a new matrix where we swap this diagonal, okay, the A and the D, we swap them, DA, and then we put a minus sign on the other elements. So it's going to be minus B minus C. Okay, this is the inverse of the original matrix. Okay, so first homework question. Show that this is in fact the inverse. Okay, so that's our first homework problem for today. Okay, so this is for a 2 by 2 matrix. A 3 by 3 matrix is a bit more complicated, but it's not too bad. Let's go through that using an example. So finding the inverse of a 3 by 3 matrix. Okay, now there's no simple rule like with the 2 by 2. So 2 by 2, you can do it on one line if you want. For a 3 by 3, there's a couple steps that we need to know. Okay, so again, the first thing is checking the determinant. So let's say we have a matrix M. It's given by 1, 2, 3, 0, 1, 4, 5, 6, 0. Okay, so we need to check the determinant. So the determinant of M, or remember, we could write this as 1, 2, 3, 0, 1, 4, 5, 6, 0, like that. Okay, this is going to be 1 times, we block off that column, we block off that row, and we find the determinant of the smaller submatrix. So that's going to be 0 minus 24. Then minus 2, because that's the next element. Remember, there's the minus sign. Okay, we block off that column, we block off that row, and the determinant of the little submatrix, that will be 0 minus 20. Plus the last element, that's a 3. We block off that column, we block off that row, and we take the determinant of the submatrix. So that's going to be 0 minus 5. Okay, you can work this out. This is going to be 1. Now, it doesn't matter what positive value, negative value, that doesn't matter, as long as it's not 0. Okay, so in this case, it's not 0. So we can proceed to find the determinant. Okay, so you can call this step 1, find the determinant and make sure it's non-zero. Step 2 is to find the transpose of the original matrix. So M transpose, that's going to be, we're going to swap the rows of the columns. So 1, 2, 3 along the first row becomes 1, 2, 3 down the first column. 0, 1, 4 along the second row becomes 0, 1, 4 down the second column. 5, 6, 0 along the third row becomes 5, 6, 0 down the third column. Okay, so we've taken the transpose. Okay, good. That's the second step. Now, the third step is to find a whole lot of determinants of the different submatrices. Okay, so what do I mean by that? Well, first, I'm going to block off the first row and the first column, and that gives me a little submatrix, the 1640 submatrix. So I write that down, 1640. As a determinant, calculate that. That's going to be minus 24. Okay, so that's the first thing. Now I move on to the next element. That's the 0 there. So I block off the 0 column, I block off that row, and I look at this submatrix. So that's going to be 2630. Okay, so 2630, I work that out. That's going to be minus 18. Yeah, good. Then I do the same thing for the last one. Block out that column, block out that row. I get a little submatrix and I find the determinant. 2, 1, 3, 4. Okay, so that's going to be 5. Okay, so that's taking care of the first row. Now I do exactly the same thing for the second row. Okay, so let's do that. Block off the row with the 2 and the column with the 2, and I look at the submatrix there. So that's going to be 0, 5, 4, 0. That's the bits left over. That's going to be minus 20. Okay, oops, let's rub that out. Next one, block off that column, block off that row. And then the determinant of 1, 5, 3, 0, that's going to give me minus 15. Okay, and lastly, block off that column, block off that row. The leftover part is 1, 0, 3, 4. And that's going to be 4. Okay, so I think you get the idea, and you just complete this for the remaining last row there. Okay, so let's just go through that quickly. If we block off that row in the column, the leftover will be 0, 5, 1, 6. That will give me minus 5. You can check the remaining 2. It's going to be 1, 5, 2, 6. That's going to give me minus 4. And the last one is going to be 1, 0, 2, 1. And that's going to give me 1. Okay, so we should end up with 9 determinants here because there's 9 entries to this matrix. Okay. Next, we form the adjugate matrix. So we call it ADJ. Okay, the name doesn't matter, but it's a new matrix that we come up with of M. Okay, so what we do is we take all these entries and we put them into a matrix. However, the alternate entries we need to multiply by minus 1. So what do I mean by alternate entries? So the first one we leave alone. The second one we multiply by minus 1. The 5 we leave alone. The next one here we multiply by minus 1. The next one we leave alone. The one after that we multiply by minus 1. The next one we leave alone. Next one we multiply by minus 1. And the next one we leave alone. So you see it forms this kind of pattern here where these entries in green, okay, you multiply those green ones by minus 1, and the other ones you leave alone. So the ones in blue, you don't touch those. The ones in green, you multiply by minus 1. Okay, so you see how they alternate. So blue, green, blue, green, and so on only the green ones you multiply by -1. Okay, so if we do that, we're going to get the following matrix. -24, 18, because we multiplied by -1, 5, 20, because we multiplied by -1, -15, -4. Okay, again, because we multiplied by -1, -5, 4, and 1. Okay, so this is the new matrix that we get after multiplying alternate entries by -1. Okay, so this is step 3. Oh, you can say this is step 3. You can call this step 4. Okay, step 5, and the final step is now finding the inverse. So M inverse is now given by this new matrix that we found divided by the determinant of the matrix. Okay, now the determinant was 1, so we're just dividing by 1. So that means the inverse is just this matrix here. So -24, 18, 5, 20, -15, and -4, -5, 4, and 1. Okay, so that's our inverse for M. Okay, so second question for homework. Show that M times M inverse is equal to the identity. So that's part 1. So this is with right multiplication by M inverse. It should give us the identity. And number 2, M inverse times M is equal to the identity. This is with left multiplication by M inverse. Okay, both ways should give us the identity. Okay, any questions so far? Okay, another homework question. Find the inverse of 102, 3, 4, 1, 1, 1, 5. Okay, so we've got this matrix here. Find the inverse of the matrix. If you can't find the inverse, explain why you can't find the inverse. Okay, so remember those steps that I told you about. Okay, so now we know how to find the inverse of a matrix. Why is this useful? Okay, so we're going to be using this inverse of a matrix to solve those linear systems that we saw a little while ago. Okay, so let's get ourselves a system that we had earlier. Here we go. Okay, so we looked at this before, the system here, and we got ourselves a solution. Sorry, not this one. Here we go. Okay, so this one looks nice. So it's going to be x plus y plus z is equal to 6. 2x plus y minus z is -3. And 0x, so nothing there. So 0x plus 3y minus 2z is equal to 0. Okay, so this is a system we looked at a while ago, and we found the solutions 1, 2, 3. Let's try and solve this, not using the row operations with the augmented matrix, but instead by looking at the inverse of a matrix. Okay, so how do we do that? Okay, so let's rewrite the system. We've got x plus y plus z was 6. 2x plus y minus z is equal to minus 3. 0x plus 3y minus 2z is equal to 0. Now, if you wanted to solve this using the previous method, you would write this as an augmented matrix and then do row operations. However, we could also write this using matrices. So we can write this system of equations, so multiple equations, as a single matrix equation. Okay, so how do we go about doing that? Well, remember how matrix multiplication works. You do the dot product with the rows and the columns of A and B if we're multiplying them. So take a look at this matrix multiplication here. Okay, if I have 1, 1, 1, 2, 1, minus 1, 0, 3, minus 2 as a matrix, so these are the coefficients of the unknowns x, y, z. If I take this matrix and I multiply it by x, y, z as a 3 by 1 matrix, so we've got a 3 by 3 matrix, we've got a 3 by 1 matrix. Let's multiply this out and see what we get. This is going to give us another 3 by 1 matrix. Let's see what we get. If we do the dot product of this row with this column, we're going to get 1 times x plus 1 times y plus 1 times z. In other words, x plus y plus z. Let's do the dot product of the next row with that column. Okay, so we're going to get 2 times x plus 1 times y minus 1 times z. And if we do the multiplication, the dot product of the very last row with the column, we're going to get 0 times x plus 3 times y minus 2 times z as a 3 by 1 matrix. But that's exactly the left-hand side of our equation. So what we want is this to be equal to minus 6, minus 3, and 0. Sorry, not minus 6, just 6. 6 minus 3 and 0. Like that. Okay, so what we've done is we've turned this system of equations into a single matrix equation. We can write it a bit more neat as the following. 1, 1, 1, 2, 1, minus 1, 0, 3, minus 2 times x, y, z is equal to 6 minus 3, 0. So this is something like A times B is equal to C. We've got a matrix A, which is a 3 by 3 matrix, a matrix B, which is a 3 by 1, and lastly, a matrix C, which is a 3 by 1. And what do we want to solve for? We want to solve for x, y, z. We want to solve for this. Okay, because that gives us our solutions. In other words, over here, we want to solve for B. So how do we solve for B? Well, remember back to the beginning of the lesson, if we want to solve for B, we need to undo the multiplication by A. So we're going to have to do left multiplication on both sides by A inverse. Okay, the A inverse and the A on the left-hand side, they cancel. So we get B is equal to A inverse times C. And that's how we can get our solution. If this matrix A is invertible, we can multiply both sides by the inverse and we get ourselves the solution. Therefore, XYZ is equal to the inverse of that 3 by 3 matrix. So let's just write it as 1, 1, 1, 2, 1, minus 1, 0, 3, minus 2, inverse times 6 minus 3, 0. And that gives us our solution after doing the multiplication, of course. So this is a new method of finding a solution to a system of equations, provided it's invertible, right? We can't do it if it's not invertible. So this needs to be invertible. So you do need to check that as well. Okay, but we'll see. We know that there's going to be one unique solution because we did this already. So we know that this matrix is invertible. Okay, because we can get a unique solution from it. Okay, if it's not invertible, then we have some issues with that, but we will take a look at that on Friday. Okay, so final homework for today. Find this inverse. Okay, using the method we had before. Remember, you check the determinant, you do the transpose, you find all those 9 determinants, and then you got your final matrix from there. Okay, so find this inverse using that method, and then solve for x, y, z. Okay, so that's the last bit of homework there. Oh, someone says here, I think it's 2x minus y minus z equals minus 3. Let's have a look. Oops, sorry, too far back. 2x minus y minus z. Yep, you're right. Let's just fix that. That's okay. Let's just fix that here. So that's a minus. That's a minus 1 there. That's going to be a minus y here. There's a minus 1 there. And a minus 1 there. Okay, so this matrix should be correct now. Okay, so if we use this matrix here, if we find that inverse and multiply it across, we should get our solution. Okay. Thanks for spotting that. Okay, are there any questions about what we did today? Okay, so this was just an introduction to show you what we're going to be doing for the next few lessons. So tomorrow we will go through a few more examples, okay, just to go through the method a couple of times. And then next week we will look at what happens if the matrix is not invertible. Okay, so like I said earlier, if this matrix is invertible, we can just multiply it across and we get our unique solution. But we know that sometimes there is no solution and sometimes there are infinitely many solutions. Okay, so what happens then with regards to this invertibility and number of solutions? Okay, so we're going to have a look at that next week sometime. Okay, if you would like to do some more examples on this, tutorial 4 has a few questions on testing invertibility using the determinant. And I think question 2 from tutorial 4 is finding the inverse. Okay, you can have a look at that if you want some more practice. Okay, if you do have any questions later on, just post them on the WhatsApp group. I'll be happy to answer. You can ask the tutors, okay? They can help you, or you can send me an email. Okay, but I'll see all of you tomorrow for some more examples on this. Okay, bye everyone.